Now that you know about waves and its different types, let us go on deeper to the concept or theory of the first component, mechanical waves. We will be covering the following objectives as we go through today's module: the difference between transverse and longitudinal waves, as well as its similarities, frequency of waves, and the resulting product of wavelength and frequency. First up, transverse waves. Transverse waves are which the vibration of the particles or medium in which it travels are at right angles to the direction. Water waves are an example of transverse waves. Now, let me screen an illustration. The animation shows that the rubber duck only moves up and down, while the energy of the wave moves along the tank. In other words, the energy it travels to or propagates is perpendicular to the direction of the wave. Also, as seen, the energy, however, is passed along the water from one wave to another. Up next, the diagram gives a side view of a transverse wave, which consists of high peaks known as the crests and low parts known as the throws. The distance between two successive crests or throws is the wavelength. The horizontal line indicates the undisturbed water position. The height of the crest from the undisturbed water position, or the depth of throw from the undisturbed water position, is the amplitude of the wave. And that sums up the features of transverse waves. Now, let us move on to the next form of wave, the longitudinal wave. These are waves in which the vibration of particle or medium in which the wave travels are in the same direction as to that in which the wave travels. Sound waves are an example of longitudinal wave. Let me screen an illustration. From the animation, it shows that sound waves travels through air. Energy is passed along the air molecules by lengthways of vibration of the air molecules. Thus, air molecules only move through and fro or forward and backwards in the direction of the travel of the wave. The sound energy is transferred from one molecule to another and so travels along the wave. Now, the diagram shows the side view of longitudinal waves. It is made up of regions where there are molecules that are closer together and have a higher particle density known as compression, and regions where the air molecules are further apart and have low particle density known as rarefactions. The region of compression is at a slightly higher pressure due to the air molecules pushed together, whereas the region of rarefaction is at a slightly lower pressure as the molecules are further apart. The wavelength of a longitudinal wave is the distance between successive compressions or rarefactions. The amplitude is the maximum distance the vibrating particle travels from its undisturbed distance. And now, let us recap the differences and the similarities of these waves. Up next, it is essential to understand the frequency of waves. The frequency of wave is a measure of the number of waves made by a source each second, or the number of waves that passes through a particular point in the medium each second. The SI unit of frequency is in hertz. Now, let us then relate the frequency and wavelength. The product of these two components results to the velocity of waves. And that wraps up our lesson for today. On our next module, we will cover the pyramidal formula of waves.